All right. Now we're gonna start. How you guys doing? Everybody all right? So today is day 9. Um, so we're gonna go. Oh, there's homework up. It's due tomorrow. These are last week's notes or yesterday's notes. What are we doing today? Today we're going to finish spirals, and we'll do. And if I get to it, we'll go over demographics. I'm actually let me do something a little differently. You all got such great questions. It's 2 days worth of questions, so I'm not going to go through all of them today at once. I'll go through the ones that I was supposed to do the other day. So I'm a little behind on these questions, and then I'm going to talk about all that stuff, and then I'll talk about your questions on demographics, and then I'll talk about demographics. Let's see. Let's just start going through questions. So first off, what's a Gaussian? So I went through that in kind of detail on Tuesdays. So I just left it up here because that's how I was doing things. Does anybody else want me to talk more about Gaussians in general at the moment? Feel free to. When you have a specific question that isn't like, I have a question about the Tully-Fisher, but it's about, I have a question about this thing. Page numbers are helpful because sometimes I forget what he called something or whatever. So not strictly necessary, but if you're asking about a specific equation or a specific wording in the text, if you could put the page number, that's helpful. Not a huge deal, but okay, so one of you asked the first paragraph on page 112. Either that's about the anisotropy. I'm not sure what you meant by the first paragraph because it's the middle of the paragraph starts in the middle of the page, or the previous page. So it's either that question is about anisotropy, which I did day before yesterday. No, Thursday. It's Tuesday today, right? Last Thursday. Or it's about the relaxation time, which I'll get to. Immediately following that question was a question about the relaxation time, which I'll go through in detail today. So several of you had questions about that relaxation business. The Jeans equation. So this is something that I had actually not realized was in this text, because this is the first time anybody had ever asked about it. But what this equation says is actually useful and interesting, so I'm going to spend a minute and talk about it. I forgot to write down notes, so I'm going to wing it, and so I might screw a thing up. That's always true, though. So the book says, what the book is talking about with the Jeans equation. So the Jeans equation, Jeans shows up, he's got his name on all kinds of stuff throughout star formation and stellar structure because he did a lot of this work. The Jeans equation is about if I have an elliptical galaxy, and I think it holds for spirals as well, but it's mostly for ellipticals because they're roundish. If I have a radial velocity, now, okay, when I say radial velocity, sometimes I mean relative to me, but this time I mean relative to the galaxy. That makes sense? So the radial velocity that I, as an observer with a telescope, can measure is the velocity along my line of sight. But this is the velocity relative to the radius of the gas, just like if you're in spherical coordinates, you've got r theta phi, this is r. So if you've got some radial velocity, you also have some theta velocity and some phi velocity. So you got some velocity going this way, and you got some velocity going this way. Now, each of these things is a distribution. So we've got the radial velocity for a bunch of particles, and we've got the theta velocity for a bunch of particles, and we've got the phi velocity for a bunch of particles. So we need to talk about the statistics of these quantities, because just talking about the distributions themselves is hassle. So working with distributions is hard. Working with numbers is easy. So so he defines this parameter beta. Now we're going to use beta to mean a whole bunch of things throughout your lifetime as an astronomer. So beta only ever means anything in that immediate moment that you're talking about. Beta will mean something different in like 35 seconds. So this beta we're defining as 1 minus VR, the average of VR over the average of V theta. And I think you might have squared these. I can't remember exactly. And it's not in my electronic copy of the book because this is a newer edition of the book. It's something like that. Oops. Sorry, I remember how I defined it. It doesn't matter a whole lot, so this isn't a thing that you need to worry too much about. But I do want to explain the base concept, so the details of the math I don't care too much about. So we define this quantity beta, which is 1 minus the dispersion in the theta velocity over the dispersion in the radial velocity. And we're assuming that that the statistics of V theta equals the statistics of V phi. So okay, square angle brackets means average. So the average of the V theta is the average of the V phi. Both of those, since there's not any bulk rotation, the average is going to be 0. The second order moment is going to give you the dispersion. The third order moment gives you the skew, and so on and so on. So we'll say that the statistics are the same. By that, I mean the moments are all the same. So the nth average of this, if they're all the same, then the two distributions are the same. So we assume that V theta and V phi are basically doing the same thing. So the only thing we need to worry about is how much in and out is going versus how much round and round is going. Does that make sense? These are technical terms. So we've got how much is the radial velocity, how large is the dispersion in the radial velocity versus how large is the dispersion in the rotational velocity. Right? So if the thing is isotropic, then V theta equals VR at beta equals 0. Does that make sense? If the thing is rotating like a solid body, so it's just everything is rotating in a circle, then VR is going to be 0, and this will be minus infinity. And if the velocity is purely radial, so everything is just going towards the center and then back out again, then beta equals what? 1. Because this is 0. This isn't like the Hubble parameter or any like real constant that really has a lot of history behind it. It's just a thing that we're writing down. So the important business, so he says this, so he defines this quantity beta. Now I want to talk about this because in an elliptical galaxy, you've got all these stars that are rattling around. They've got this random motion. They've got some radial velocity. They've got some rotational velocity. What we want to do is so we're going to do some stuff with rotational curves with spiral galaxies in a second. We want to do something similar, but what this whole Jeans equation thing is saying, the whole purpose of this section is saying it's too difficult to just back out the rotational velocity because we have this radial velocity in the mix, and it's probably about as large as the rotational velocity. With a spiral galaxy, the radial velocity is really small for basically everything. Everything is going around in a circle. And you can tell that because it's flat. So it's flat, so all of the velocities are basically doing one thing. They're all basically going around on their respective circles. And the radial component's not too bad. So a lot of what I'm going to say doesn't matter for spiral galaxies. But for elliptical galaxies, you can work through this thing called the Boltzmann equation. Which, once I get through the questions, I'll probably go through Boltzmann for a minute. Mostly because it's fundamentally important, but also it's confusing as hell and takes forever to really get your head around. So I'm going to talk about it, but I'm not going to really ask anything of you about it. So what the Boltzmann equation says, I'm not going to say that. What the Boltzmann equation gives you, after you work out a bunch of math, is that the average of the square of the circular velocity, this is the rotational velocity, this is equal to minus gm over r by virial theorem. And this is equal to the square of the radial quantity plus these logarithmic derivatives, the logarithm of the density relative to the logarithm of radius plus d log vr squared d log r plus 2 beta. So this is kind of a horrible equation, and I don't expect you to understand where it came from, but I do want to point out some things about what it says. So where did it come from? Magic. We'll have to talk about where it came from later. But what it says is that the circular velocity, which we want to set to gm over r because of virial, is equal to VR squared times this logarithmic derivative of the density, that's not a big deal. Logarithmic velocity, not a big deal again. Here's beta, that's a big deal. So now the amount that it's going around for virial theorem depends on how much it's actually going around, but also how much it's going in and out, and the ratio of how much it's going around in and out. So if I want to measure this, I've got these two parameters, VR and beta, that I have to sort out. So the upshot of this is it's harder to back out how much dark matter is in ellipticals just because it's harder to do. So when I have a spiral galaxy, if I see this wave motion, I know that's going around in a circle motion. That's super hand wavy, but I mean literally I'm waving my hands, right? Whereas here, if I see velocity coming at me, I don't know if that's part of a radial velocity or part of a tangential velocity. So it's impossible to sort out, to disembody or to disentangle how much is radial velocity versus spinning around velocity. So it's harder to sort out how much dark matter is in elliptical galaxies. That being said, it has been done, and this was sorted out in like 1915 or something, super long time ago. Which is why you don't hear about dark matter in elliptical galaxies as much, but there's plenty. Okay. What's a break radius? So one of the things that this book does is he defines things backwards. So he'll talk about what a thing is and then tell you the word for it at the end of the paragraph. So sometimes, or a lot of the time, if you get to a term that he feels like he just kind of invented, check back at the beginning of the paragraph, and a lot of the times he's defined it kind of implicitly. So for this one, the break radius isn't like a thing that's like Hubble constant. It's not a universal property. It is where this thing breaks that he talked about earlier in the paragraph. So I had to read the whole thing to know what he was talking about. So what he was talking about there, let me get to that, was that there's a break in the radial distribution of light in spiral galaxies at a certain radius. So if I have a galaxy and I'm looking at the brightness as a function of radius, it does this and then it does that. So it falls off with one law, and then that law breaks, and then there's another law. There's another power law. And so wherever that knee is what he means by the break radius. That's not like a universal property. That's just the thing he happened to be talking about in that paragraph. He talks about lower limit of what? Okay, so the question is, in the section where he's talking about how big the dark matter halo is. So galaxies, all galaxies, are big balls of dark matter with a galaxy in the middle. Kind of like Kinder eggs, but not like Kinder eggs. because the dark matter ball is much larger than the galaxy. Uh, so how far out does that dark matter go? And the purpose of this section, he says, if you look at the stars, the dark matter cluster, the dark matter potential has a lower, an inner radius of 30 H inverse kiloparsecs. So that means that it's at least as big as 30. But then if you look at globular clusters, you get a lower limit of 100. So the better lower limit is the larger one, but it depends. The lower limit that you get in that paragraph, what he's talking about is the lower limit that you get depends on how you're measuring it. But at the end of the day, the dark matter potential is enormous. And we're not really sure how far out it goes. And that's weird because it just keeps going out. For external galaxies, you can sometimes tell when they're in a cluster. Then you can really tell. In clusters, you can tell where the stuff is because stuff is moving around better. Fiducial galaxy. Fiducial just means test galaxy. So that just means the kind of cartoon example, the one that I'm comparing everything to, or the things that I'm comparing everything else to. What is L15? This specific abundance business is another place where he defines everything kind of upside down. So he defines the specific abundance, then he just starts talking about SN, but doesn't ever say SN is the specific abundance that he means. So he's a little opaque in that. So SN, he says in the text, is the number of globulars over the number of globulars in an M15 galaxy, where the galaxy has a brightness of 15. So MV for my test galaxy is minus 15. So I'm going to say my typical galaxy, my fiducial galaxy, my test galaxy that I'm thinking about has a brightness of minus 15. I want to scale all of my globular cluster counts to a galaxy of this size so I can tell, well, okay, is the galaxy, so the question is the number of globular clusters just proportional to the mass of a galaxy, or is it more complicated than that? So we just take this normalized number, which is the number of globular clusters, divided by the number of globular clusters in a typical galaxy like this, times the luminosity of my galaxy over the luminosity of one of these galaxies. So I'm just taking the number that I get and I'm scaling it relative to the other things so that we can compare them all. Little galaxies don't have very many globular clusters. Bigger galaxies have a buttload of globular clusters. So is it just bigger makes more, or is it more than that? And it turns out it's more than that. Bigger galaxies have more globular clusters than you would expect just by their brightness. So that's kind of cool. And I wonder if there's a way to get a galaxy mass by counting the number of globular clusters, because that if there's something else going on, then maybe you can get that. So this number, this normalized count for my galaxy, is going to be the count that I actually have, divided by the typical count, multiplied by my luminosity divided by the typical luminosity. So we're just doing a ratio rescaling. We're just rescaling based on the ratio of the light, which is proportional to the mass. Or we hope. Or it isn't, but we want it to be, so we'll pretend. Boxiness and diskiness. I decided I really don't care about boxiness and diskiness. The upshot is you do a Taylor series on the ellipse. So if I have an ellipse, I can make Taylor series of that. And some of those terms make things boxy, and some of them make them round. So if the terms that make things boxy are large, then it's a boxy galaxy. But it really just comes out of the Taylor series. Units. So one of you, a couple of you had said that you had some trouble with getting units right. So the upshot is just be consistent, and that'll get you there. So what do I mean by that? So if you start doing something with grams and seconds, make sure that all the constants that you have grams and seconds in them, and just do the accounting carefully with the units to make sure that everything actually cancels out, because we use several different unit systems in this class. I like masses and solar masses, but sometimes in grams, and I like distances in parsecs, but sometimes AU, and sometimes light years, and sometimes centimeters. So there's a lot of, and time's usually in seconds, because it doesn't really do anything weird, and either you're short compared to a second, or you have a buttload of them. But for time, typically use seconds. And then in the end, your output, it's easiest for me if you keep things in solar masses and parsecs, because that's what I have intuition for. Someone also asked, I struggled a bit with what equation to use when. I don't have a good general answer other than come to office hours, because I will answer those questions. Or email me if you're stuck and you're like, I don't know which equation to use on this. So that's answer one. Answer two is a little bit more nuanced. So the question is, I've got all these equations, and how do I know which one to use for the problem that I've got? So the problem that I have has whatever, I'm trying to relate binary distances, the binary separation to distance here, or I want to use the relationship for finding supernova. So I've got a supernova that goes off. I want to know how bright it is. So try to think about equations not as black boxes that you dump stuff into and out comes answers. Think about them as sentences that exist just by themselves. They're just statements about relationships between two things. And I can say Frank is my dad in 19 different ways. Francis is my father, or whatever. I can take that same idea and rewrite the sentence in a bunch of different ways, but the connection between the concepts is what you should try to be thinking about when you're looking at these equations. So think about this equation. It says blah, it is relating, this thing is the absolute brightness, this thing is the apparent brightness. Now what are those things? Think about what those things are. So that's the important thing, I think, is try to make an equation not be just a blob of symbols, because that's not useful. Try to make them about connections between relationships, and try to get your head around what this equation relates A and B and C and D. I hope that helps. If not, office hours, or email me. What's an isophote? ISO means what? Like isothermal or isobar. What's that?
Uniform.
Yeah, it means it's the same. And phote is. What's that? Light, like a photon, or this photosphere, or a photograph. Now you know Latin. So these are constant curves of constant light. So when you take a so you can sort out what that means, constant light, but what is the context? And that's really an important bit. When I have an image of a galaxy, if I had a nice pencil, I could draw that curve lighter and this curve like that, and I could blend them. It doesn't work in this case, it does with pencil. So you can blend them and make a continuous, smooth distribution of different brightnesses, where the brightest bits are in the middle and the dimmer bits are outside. But it's really hard to do math with smoothly varying things that just kind of softly go from one end to another. So what we do is we draw contours of constant brightness around the galaxy. So we say, okay, here are my constant brightness curves. This one's at whatever. This one's at the next level down. This is the next level down. So that I can say, well, within this isophote, that means that within this level of constant brightness, I feel like I understand what's going on inside the galaxy. Or within this isophote, the mass is blah. The total brightness is whatever. So it's just a way to describe various parts of the observed galaxy. So you get an image from a telescope, and you can look at the isophotes on that. Does our galaxy have a classical bulge or a pseudo bulge? It is a big old classical bulge, near as I understand. In terms of galactic evolution, how far along is the Milky Way? So I love this question. I think it's a great question. I also kind of hate this question because that's not how evolution works. It's not going to an end point someplace. It just is where it is. This is where the Milky Way is in its evolution. Maybe it will do other things. Maybe it won't. Very different from Pokemon. So Pokemon have a start configuration, and then they have a next configuration, and they have a final configuration, right? And they call that evolution, and that was really, I wish they had called it something different, because it really has corrupted how people view how evolution works in a lot of different ways. But it's a really good question. Nobody's ever asked a question quite like that before. So I have a third answer to that, to this question. The question is how do galaxies evolve in the first place? How do galaxies evolve at all? And really, galaxies evolve primarily through mergers. So there's two kinds of evolution for a galaxy. There's passive evolution and there's dynamic evolution. So passive evolution is the galaxy sits there and the stars burn out. And that's how the thing evolves. So the stars do their thing. Big stars don't live very long. Little stars live forever. So the galaxy will evolve, and the big stars will explode and do their thing. And then everything gets red, and then the galaxy kind of calms down. And eventually, we're going to merge with Andromeda. So Andromeda, we can see it coming. It's coming at a significant fraction of the speed of light. I mean, it's like 0.1%, but that's still a lot faster than I drive to the store. So it's coming at us really fast, and it's going to hit us, and then we will become one of these tidally disrupted galaxies. Oh, I should have brought up some pictures of those. There's a whole catalog called the ARP catalog of distorted galaxies and weirdo galaxies, and most of them are mergers. So passive, we'll just very briefly write stars burn out, and dynamic is collisions. So we live in this cluster, so that's kind of the near-term future. So the very near-term future is the stars will dim. The slightly less near-term future is Andromeda will smash into us, and then we will turn into some kind of tidally disrupted galaxy. And then I would bet you $1. Is that? Yeah, like one of those guys. So let's see. If my internet shows up, maybe I can. How is my internet doing?
Sorry. Let me go back to the travel.
Let's see. Let's try this.
Looks like a giant shrimp.
Yeah, I know. It's not as
The shrimp galaxy.
Oh, my internet is working. So it's the Atlas of Peculiar Galaxies is the ARP catalog. So these are really all, most of them are are spirals like this. So here we have a couple that are getting tidally disrupted. Here we have a ring galaxy because something went through it. Here we have two merging galaxies. And I would bet $1 that with less than 5 minutes of Googling, you could find some good simulations of Andromeda and the Milky Way colliding, so we can see what the long-term evolution of that is. Somebody should remind me of that when I have a good internet and a minute to dig, that I should go look at that, because that's an interesting question. Okay. What is the status of dark matter halos? It's basically the way it is in the book. So there's not a big body of new measurements. There's lots of details, but the book isn't that old as far as what is the dark matter halo of the galaxy. What's up with the units in the Schmidt law? So I'll talk about the Schmidt law in detail when I go through. I'm not going to talk about it now. I'm going to talk about it when I talk about star formation next week. But it says, let's talk about it for a second. Why do I gotta look up there? The surface star formation rate, and then he's got all this crap in the bottom. Solar masses per year per kiloparsec. So this is forcing the units to be a certain way. So what he's doing is saying, I can measure the specific star formation rate, and I can measure that in grams per second per square centimeter, or, which is a dumb number for stars, or I can measure it in solar masses per year per square kiloparsec, just 1 year, per square kiloparsec, which is a better unit to do it in. But all he's doing here is he's forcing the units on this to be this. That makes sense? I'm dividing out the units, and I'm left with a number, and that number is with these units. Equals 2 times 10 to the minus 4 times the surface gas density in units of solar masses per parsec squared. To the minus 2. So solar masses parsec to the minus 2. So what does this say? So sigma SFR, so this is in a way defining what sigma SFR is. You see why? Just from the units. So it's defining that sigma SFR is some kind of mass. Are you guys looking at something cool?
I think I found it. I'm not sure if it's right though.
Oh, cool. Hey, can you screencast that? Yeah, probably not. You're probably not on the right one. That one's probably not.
Is it even the right one?
I mean, is the right galaxy, the right collision?
The right, yeah, it's fine.
I mean, that's about right. I mean, but I've never seen that happen, so I'm not gonna say for sure. I would assume if you found something that said Milky Way Andromeda, because all you need is the two masses, 2 rotations, and 2 angles. So you just need the relative angle of the Milky Way and Andromeda. We can sort out what that is.
So this
And the masses and the distances. So, and then there's like codes you just plug those in. That's awesome. Could you email that?
Yeah.
So, and then we'll put it on the screen next time. This is the formation of stars. This is the star formation rate. It's how many solar masses you form per year per square kiloparsec, per area of the galaxy. So I've got my galaxy, it looks like this group. Schmidt law is for spirals. You know that already, though. Why do you know that already? Was that?
That's the only place like star formations happen.
That's right. Ellipticals aren't forming stars. That being said, I think that somebody's probably grafted it onto it because it's kind of an obvious thing to do. But Kennicott and Schmidt did it for spirals. So Schmidt did it first in like 1958. And so he's the first person to measure this relationship or talk about this relationship. Rob Kennicott is alive now. He's somewhat older than I am. And he did this again in the late 90s, and his papers are some of the most highly cited papers in astronomy. They've got like 4,000 or 5,000 citations. Just because he did such a good job and really codified how we're thinking about this. So we're thinking about the star formation as a function of area. So if I take an area of this size, I'm going to get one star formation rate. If I take a bigger size, I'm going to get more star formation just because I got more stuff. It's an extrinsic property. So we want to get rid of the size with this, and we want to get rid of the time. So solar masses per year is the star formation we want to normalize by the area of the galaxy. This is equal to the surface density of the gas in solar masses per square parsec. Why is this kiloparsec and this square parsec? Well, star formation rate's in low numbers, so we'll use a big area. So this is just another way to get the density of the gas. So what this says is how many stars I get is proportional to how much gas I start with, kind of. I'll go through this in more detail later. But that's, so the question was about the units. So I wanted to actually talk about the units, but then I figured since the units are telling us physics, we'll get physics out of what these units are telling us. Where was I? Oh, they're really going to take me the entire class to get through questions. I don't mind doing that if it bothers you, if I'm just talking about your questions. But I like the questions. I think they're really very valuable because they connect things. They make things connect. Let's see. Oh, and there's important bits like you guys complaining about the reading, which I appreciate. Because sometimes the readings are too long. I think this reading's too long. I need to make it more than one reading because this is taking people like 3 or 4 hours, which is longer than my goal. So what to do if I do that? Just read it fast, and I'll try to make them shorter in the future. But what to focus on? That's an important question. That question doesn't change. Because I'm still going to be giving you more readings than what I'm covering in class. So go through the readings like everything's basically the same in level of importance. Don't spend too much time on it. Just get an overview. This is like a primer coat. You're just putting a coat of gray on your car so that you can paint it a nice color in a minute. I just want you to get the basic ideas. I don't expect that you're going to go through the readings and actually understand all the details. We'll talk about those. That's what class is for. So not everything is relevant, and I will not ask you questions from the reading if I don't talk about it in class. So don't feel like you've got to pick up every bit in the readings. So if I talk about it, I care about it. There are a lot of things in there that he talks about that I think are interesting, and I would spend all my time, but I would never get anywhere if I talked about all of the stuff in the readings. Yeah, hope that helps. I'll try to make the next ones kind of shorter because this reading was too long. As is evidenced by how much time it takes me just to get through the questions. How do astrophysicists study dark matter in galaxies? That might be like question 1 on the final. It's a good question. There's really a lot of what I'm talking about, not just now, but also going forward. So we'll talk about rotation curves for a second. I haven't really introduced those yet, so I'll talk about rotation curves a little bit today. We'll talk about other ways to measure dark matter in the future, but basically it's about this. It's about looking at the photons and then looking at the dynamics, and it's comparing the light that we get from the dynamics that we get, and when they're different, then there's got to be something missing. Do SO galaxies have isophotons? Yeah, all galaxies do. It's just a definition. It's just a line you can draw. Now, you can't always draw nice, smooth lines, but with an SO galaxy, I don't think they're as complicated. A couple of questions about quasars, which I'm going to punt for about 4 weeks. But I'll answer them real quick. Why do quasars emit radiation through the entire electromagnetic spectrum? Because they're ultra-violent and ultra-large and really hot. So there's a huge amount of general relativistic violence happening.
And in all of that, the gas gets incredibly hot. And when there's a bunch of energy, there's a bunch of energy output. And are they the most luminous thing in the universe? I don't want to say most luminous thing in the universe, because I bet that there's a gamma ray burst that probably outshines the quasar, but I don't know if that's actually true. They might be. Probably on par with. So I don't like speaking absolutes, but yes, they're the brightest things in the universe. Now, you might find one thing that is brighter than something else, some weird explosion. Neutron star mergers might be brighter. I'm not sure. But none of those things last very long. None of those things last very long. Quasars are the brightest things that stick around for any period of time. Anything brighter lasts for a couple of weeks at the most. Is extinction the reason that starbursts are reddish? Yes. We'll go through that in detail later. One of you asked about the bimodal color distribution, which I then spent a bunch of time on. I can spend more time on it later, and that person isn't here. Red galaxies have higher absolute magnitude than blue galaxies. Yes, that's what this says. It tells you. So the color bimodality graph shows you that red galaxies are brighter in general. And it's specific about what you mean by in general, because it's a distribution. There's wings. I'm not going to bring that up. I'm going to turn that into a homework question, I think. Let's see. Why do ellipticals and CDs follow a de Vaucouleurs profile? So the de Vaucouleurs profile is the result of virialized spheres. So if you project a virialized sphere, you get a de Vaucouleurs profile. What makes CD galaxies so bright? They're really big. Really big. That's it. Why does metallicity of ellipticals increase towards the center? Mostly because that's where the crap falls. And so as stuff's been in there for a while, it'll kind of fall, kind of like why all the dust winds up under your couch, because that's where this stuff can collect. This is the bottom of the potential well. You run out of energy, you go down to the middle of the bottom of the potential well. What does the relaxation timescale really mean? I'll do that in a minute. Maybe I'm not, actually. It's 12:25. Holy crap. Question about the anisotropic velocity distribution, which I spent Thursday on. I can do that again if you want, if there's more questions, but you gotta holler. Quasi-stationary density waves. What does that mean? I'll show you. Why do bars form in galaxies? Well, because galaxy members like to drink. I cannot stop making bar jokes. I apologize. It's funny to me. I don't really understand the formation. I don't think that the formation is really well understood. It's a dynamical thing. It's like a collective action, which you don't see a lot in these things. So, but for some reason, all the stars start going on really radial orbits. And when the stars start going on really radial orbits, they drag more stars to start doing that. They entrain a flow. So once you get a little bit of that radial motion, so it's a lot of just radial motion, not rotational motion. And that's what makes that bar structure. And it's a dynamic process. It's about the radial motion, it's not about a stick of crap like a sandbar or something. It's that they're all moving here. It's the dynamics that makes that thing happen. Explain Kennicott-Schmidt. I did. This reading was too long. I agree. Nobody actually said it quite like this, but there was definitely some comments. Why do spiral galaxies have few arms and are less homogeneous? I'm not 100% sure what that question meant, but basically, nobody really understands spiral arm count. We barely understand spiral arm formation, so they're weird things that I think it's tricky to get them to do that unless you have all the physics. So there are galaxy formation simulations that really do a great job, and they reproduce spiral arms and bars pretty well. But I still don't think that means I don't think that means we understand them quite yet. Okay. That's the end of the questions. Does anybody have any other questions on the questions? I got 6 minutes. Let's run through this real fast. So Go through the slides. Yeah. At 12:50. Oh, thank you so much. In my head, it ends at 12:35, and I can't shake that. So I'm looking at this clock, and I'm like, shit, I'm running out of time. But I'm not. I have plenty of time. Thank you. Well, okay. So now I got 20 minutes. So I don't have to go so fast. Sweet. So I'm still only going to get through spirals. I'm not going to get to the relaxation bits. I should write that on my board, on my laptop, like classes from 12:35 to 12:50, so that I stop forgetting. Okay, so basic properties of spiral galaxies. So again, the only thing that I want you to know in the text that I might not bring up, everyone, are all of the tables, especially in the galaxy section. There are a bunch of tables of stuff that just kind of dump numbers, and I can read tables to you, but that's not useful. You should spend some time with these tables so that you can really get a feeling for how big these objects are. So SA galaxies have B, so MB, what is MB? Do you think? Now, so this relates to another question from the reading. So just out with no context, what would you guess that MB means? Which magnitude? What's that? Good guess, but no. B could be bolometric, but B here means B. Blue. So this is the blue brightness. Now, okay, how would you know that? Well, from the context, it's not a mass, because it would have just said M, and usually it's solar masses. But this is a really common thing. I don't think that anything else is ever M sub capital B. So, but the trick is, with capital M, and with a lot of variables that we run into in this, we use the same variable to mean a whole bunch of different things. So mass is tricky because mass is, capital M, but so is absolute brightness. So you got to sort out by context what's what. Here it's just naked on a table. So they give you the B. You probably never make a mass sub B that I can think of. But no, that's a lie. I was going to say it's rare that there are subscripts on B, but that's entirely not true. So the masses of these, so the blue band brightness is M sub B, and this varies from -17 to -23. The other way you can tell what a number is by what its values, what values it can take. So here you can see this thing that they call MB, whatever it happens to be, has values between -17 to -23. It is not a mass. We have not discovered negative mass yet. When we do, it'll be exciting. I don't think that's happening. There's a really cool experiment going on at CERN where they're trying to measure if antiprotons fall up or not. So far, no. But, I mean, how dope would it be if antimatter went the other direction? That would be amazeballs. Anyway, it's not going to happen that way. But so to sort out the answer, so the upshot of is this a mass? What does this thing mean? Is you got to use the context a lot of the times to sort out what probably is he talking about. Is this probably brightness or is it probably mass? That's one. There are many places where that kind of degeneracy shows up. Okay, so the masses here, these are like 10 to the 9 to 10 to the 12. Giant positive numbers. This is going to be mass. So littler galaxies are like 10 to the 8, 10 to the 10. Bigger SA galaxies are like 10 to the 9, 10 to the 12. The bulge to mass, this is important, don't I? Yeah. The bulge to total brightness is an important quantity because this is really one of the big ways that they actually grade what type of spiral is what, is by measuring the bulge brightness and taking the ratio with the total brightness. SA galaxies have big bulges, whereas your SBSCs have littler bulges. So the ratio is about 0.3, and this is in luminosity. So this is the total brightness in luminosities. you get about 0.3. For smaller, later type galaxies, you get 0.1, and for even later than that, you get 0.05. So the bulge shrinks as you go along the Hubble sequence. The size gets a little smaller when you get to these little dwarf guys. The mass to light evolves. Why does the mass to light evolve? Let's talk about mass to light for a second. What is the mass to light ratio for the sun? There's this cool variable upsilon that gets used for basically nothing other than the mass to light ratio in astronomy. Nobody uses this for anything else, right? So if this is some number, let's call it 7. We'll leave the units blank so that this is a real thing regardless of what it is. So let's say that this is the mass to light for an O star. And this is 7 in whatever made up units. But it'd be something like solar luminosity, or it'd be something like solar masses per solar luminosity. But it's more than 7 for an O star. It's a lot. What is the mass to light ratio for 1 million O stars? What's that? 7. Also 7. So remember what the luminosity did with mass. Luminosity goes like mass to some large power. This power changes when you go up in mass, so we'll just leave it as alpha, but alpha is a number that's bigger than 1. It's like 2 or 5. So the mass to light is going to be mass over the mass to some number that's bigger than 1. So upsilon is a decreasing function of mass. So when we look at this, this statement here about the mass to light ratio for various kinds of spiral galaxies. SA galaxies have a mass to light ratio of about 6, whereas SC galaxies have a mass to light ratio of about 2. What does that tell you about the stars? Lower mass to light ratio, bigger stars. Bigger stars. Bigger, more massive stars give you more light per mass. So, these stars, and this is just a simple number, these stars, this simple number tells you that there are more big stars in these kinds of galaxies than in this kind of galaxy. Now, dark matter also matters, so there's that. That's why we don't use mass to light to measure anything real, but we can learn things about the spiral galaxies that way. Let's see. The rotational velocity is about 2 to 300. The bigger ones are rotating faster because they're bigger. SA galaxies are bigger than SC galaxies on average. But not a ton. I mean, they're in this kind of range. Here, this is an important one. This is the average surface brightness. Not the peak surface brightness, but the average surface brightness. We talked about this when we talked about ellipticals. We talked about how the average surface brightness is a decreasing function of mass in big elliptical galaxies because they get less dense, so they get bigger faster than they get brighter. Spiral galaxies don't do that. Spiral galaxies all kind of have the same center, the same average brightness. So bigger means brighter. Pretty much that's how it works. Bigger is brighter. You get about the same average. You double the thing, you get double the light. So spiral galaxies don't have this this problematic structure. They're basically the same. This is called Friedmann's law. So, and really all it says is bigger is brighter. and they're proportional. So you double the mass, you double the brightness, which is different from elliptical galaxies. B minus V. What is B minus V? What kind of thing is B minus V? It's a color. 0.5 for SC galaxies, 0.75 for SA galaxies. Which one is bluer? Just from the numbers. No, the SC galaxies. Lower number is bluer. Lower number is bluer. That's the convention. All colors are that way. Lower number is bluer with every color. So lower number is bluer. SC galaxies are more blue. That jives with the more massive stars, right? Because more massive stars are bluer too. Yeah. Yeah. Roughly. Have a ballpark. So if I ask you how big a galaxy is and you tell me it's 10 to the 9 solar masses, I'm happy with that. If you tell me it's 4 solar masses, I'm not happy with that. So logarithmically, have a familiarity with these numbers. You don't have to memorize the table unless you're a table memorizing kind of person. But these are like ish numbers. These are like ballparks. So memorize them with a ballpark around them. It would be cool if he gave you errors on everything, but he didn't. Yeah. I think that's all I got to say about that. So I like this table. So one of the reasons that I like this table is it you can learn a lot about galaxy evolution by way of this table. You can learn about how galaxies go from big galaxies to little galaxies by way of this table. The bulge looks like a Devacalures, and the disk looks like an exponential, which we've talked about already. Okay, rotation profiles is probably the last thing that I'm going to really talk about. I'm going to put up some stuff about spiral arms as well. So I take pictures like this. What is this? This is a galaxy. This is NGC 7331, and this is a radio measurement. This is in H1. That means neutral hydrogen, and this is velocity map. So each one of these contours is an equal velocity contour. So I wish that I had the data for this so that I could really show you what this looks like. So when you have a radio telescope takes a picture in a dozen or more different frequencies, different wavelengths at the same time. It's pretty rad. So when I take the picture on the left, we get 11 pictures and we add them all up. And we get the total luminosity in the radio from those 11 images. For the picture on the right, we take those 11 images and we say, okay, we average the spatial position, or we average the velocity with each spatial position. So we, instead of adding them up, we average them across all the frames. So we get the average velocity at each space, at each point in space. And then we draw isocontours. So these isocontours are where the velocity is roughly constant. So what that lets you do is lets you see the velocity structure of this galaxy. So just look at this thing and tell me what it's doing. How many of you guys go camping or hiking and are comfortable reading a topo map? Read this like a topographical map. So these are equal contours. And so what do we start off with? This is a velocity in kilometers a second. So this is 1,000 and this is 640. So I am 0. Positive is outwards. So positive velocity is going outwards. So is this side coming towards me or is this side coming towards me?
Saying the upper side. Wait, I was saying the upper side is coming towards you.
That makes sense. As a lower velocity, so it's not moving away as far. So how fast is this thing moving away from us? You can read that from this graph. You can do math in your head, but you can just use symmetry and you can just read it off.
The velocity towards us or away from us?
I am 0. There's no convention here. I am 0. I start measuring from 0.
Okay.
So velocity is positive away from me.
Okay,
Velocity
okay.
positive coming towards me doesn't make any sense because that means I'm at negative infinity.
Okay, that makes sense.
Yeah.
Yes.
So positive and outwards. So this is 820 kilometers a second. This is 910 kilometers a second. This is 730 kilometers a second. So what's the bulk body? So it's spinning. Its top is coming at me. Well, let's stop thinking about the spinning for a second. Let's get its bulk motion first. What's the average velocity of this gas? 820. Does everybody see why?
Yeah.
Because it's in the one in the middle. We're going to average. We'll just average these guys. We'll do an average. If I want to know what the mean velocity of the whole thing is, I add up all the velocities and I divide up by how many I get. I only have two. I have 640 and 1,000. If I average those, I get something like 800. Similarly with these, similarly with 800's in the middle. So this is a thing that's rotating this way. And 820, this is, all this gas is just moving this way. I don't see the radial motion of this gas. Radial relative to the galaxy. I see its motion away from us. So you can really just read off the bulk motion of the galaxy as what the center is doing, which you can also see as the average over the whole thing. Does that make sense? So I can then make a map of distance from the center versus radial velocity, or versus circular velocity. And it looks like this. And I can do this with a whole bunch of stuff. Uh-oh. Got to have the power. Now you won't complain. Okay. So let's jump to this bit. So V squared equals GM over R. This is like our Maxwell's equation for this course. This is our F equals MA for this class. This is the answer for everything. So if I ever ask a question and you don't know, you could say V squared equals GM over R, and that's probably the right answer. To be glib. So, okay, what I measure is light. So I take a measurement. So I have this galaxy, and I have its rotation curve, and I have its brightness. So the brightness goes like this. So this is the luminosity in solar luminosities. Sorry. Squirrel brain provided 10 things that I didn't need to say out loud. So I don't want the luminosity, I want the mass. I want to know what the mass is doing. So the mass is the mass to light ratio times the light. Pretty straightforward. And this is an average mass to light ratio that I get based on the stellar population. So I measure the light, I make a spectrum, I say, what do I think this stellar population looks like? We understand stars really well. So we understand the mass to light ratio of all of the kinds of stars super well. So this isn't a bad thing to do, because like it's all the light's coming from the stars, and we understand the stars pretty well. So we get the mass from the light. So we measure the light, multiply by epsilon to get the mass. Right, this is the luminous mass. Why do I call it the luminous mass? Because it's the luminous mass. It's the mass that's giving off all the light, right? And I need to distinguish it from the dynamical mass. So the luminous mass is what I measure here. I then can say, okay, V squared equals GM luminous over R. R is the coordinate, so that's not a thing I measure. That's part of where I put the telescope. So this is the luminous velocity. That doesn't really make any sense. But everything adds up in like a mass, so we'll do it that way. So this is what the rotation curve of the stuff that I see should be. And then I have V squared total, which is going to give me GM total over R. So I measure this guy. Let me color code this. I measure this one to get that. I measure this one to get that. Boy, that's the squeakiest chalk. It's the worst. So I measure the velocity total to get the mass total, and I measure this with my radio telescope. just doing it back out. I measure this. I get the luminous mass from the mass that I measure for the light. Right? So then the total mass is the luminous mass, which I measure there, plus the dark matter mass, which I don't know. But I can sort it out. So now the dark matter mass is going to be the total mass minus the luminous mass. And we can sort out what this is. Or we just go measure it. Oh, I should have had the wrong camera. So if we look back at and make a plot, this is for a different galaxy. So the points are what got measured. So that gives you the total mass. So the points are the velocity measurements. So then we get this this disk. This one comes from measuring the light and saying, what do I get for the luminous rotation? So we measure all the light and we get this curve, and then this other curve is what the dark matter halo is doing. So this is the difference. The dark matter halo is r over g, which is just coordinates. The dynamical velocity, which I measure from my radio telescope, minus the luminosity, which I measure with photometry. That gives me the dark matter mass. So this right here is answer 1 to how do we measure dark matter. Right, like this guy here. And we do this for all of the galaxies, and they all do the same thing. They're flat. They're way flatter than they should be for the amount of light that we see. Not light doesn't make things flat. Light falls off. It always falls off. There's no flat light curve. More importantly, to get a flat rotation curve, you need an increasing light curve, which we don't have. So, all the galaxies show that there's a problem. So if we want to sort out what the dark matter is doing, then we can't use the light anymore because the dark matter doesn't produce any light. We have to use the dynamical mass of stars that are far out, globular clusters, orbiting galaxies, so we can use the LMC and the SMC and their properties to measure the dark matter parameters. And we see that the dark matter halo for the Milky Way is probably 100 kiloparsecs, or more. It's probably more than that, actually. Yeah, it's large. Let's see. Oh yeah, these are good. So this I started to talk about. Oh, now it's time to stop. So I started talking about this, but consume this slide. It's time to go now, so I'm not going to go into it. I'll go through this, but this slide ties together galaxy properties and star formation properties in ways that we'll talk about a lot more when we get to star formation. Let's see, the last thing I'm going to do is show this. This one. What does stationary density wave mean? This is what stationary density wave means. So you see the galaxies rotating. You see stuff coming into and out of the density wave. I think this one is a little easier to see. So you can see stuff going into it, getting denser, and then coming out and moving on to the next spiral arm. Was that?
It's kind of like traffic, where it's like traffic will like slow down, like when you build up traffic, the front goes away, then they just keep adding, so just like the density just kind of moves back.
Yeah, it's like that. Yeah, that's a very similar analogy. Okay, any other questions? I will see you guys Thursday.